The paper presents experimental investigation on mechanical behavior of sandwich structures using digital image correlation. The aim of the study is to investigate the mechanical behavior and failure mechanisms of sandwich structures composed of glass fiber reinforced polymer skins and polyurethane foam core. Digital image correlation was used to obtain far-field deformation and monitor failure evolution of the sample tested. The GFRP skins are made by hand layup technique using an unsaturated polyester resin as the matrix, reinforced by 4 layers of chopped strand matte glass fiber. The mechanical properties of GFRP skins were assessed via tensile and compressive testing. To evaluate the mechanical behavior of the sandwich structures, flatwise and edgewise compression tests were performed as illustrated in the figure on the right. In the edgewise compression test, 2 different specimen geometries were investigated to assess the influence of the length on structural performance. The curves of both tests, tensile and compression, exhibit identical behavior. 3 distinct phases are noted. Scan an electron microscopy image of this fractured zone from the specimen under tensile test reveals irregular distribution of glass fibers, a debonding of fiber matrix, and fiber breakage and pullout. For compression tests, the detected failure involved combination of longitudinal splitting, interlaminar cracking, fiber breakage, and the formation of kink bands, specifically manifested as fiber microbuckling. The load displacement curves obtained from flatwise compression tests on the sandwich structures exhibit a consistent behavior. Initially, an elastic region is observed, followed by plateau phase where the foam begins to compress, and finally densification phase characterized by a sharp increase in load with minimal displacement. As depicted in DIC engineering, the maximum vertical displacement occurs at the top plates where the load is applied, gradually decreasing to zero at the bottom fixed plate. In contrast, the horizontal displacement reflects lateral expansion of the foam in opposite directions on either side, with near zero displacement elsewhere. During the edgewise compression test of sandwich structures, densification of the foam was observed in both configurations. The tests revealed a variation in failure modes depending on the geometry of the samples. When the length of the specimen is equal to its width, localized failure modes is observed, including skin buckling, skin core debonding, shear sliding of the skin, and localized buckling followed by skin cracking. However, when the specimen length exceeds its width, the dominant failure mode shifted to global buckling, as known as Euler buckling. This mode of failure was associated with noticeable reduction on load bearing capacity. In summary, the sandwich structure with GFRP skin and PU foam core showed diverse failure mode under compression. Specimen geometry significantly influenced edgewise performance, and the DIC results aligned well with mechanical testing, confirming its accuracy.